Alright, so this is Green's theorem. So Green's theorem is a very interesting theorem itself. It kind of relates and it gives a relationship between line integrals and what we'll talk about is something called a surface integral. But for now, we have a line integral that goes from, let's say, we have a curvature, and here's our line integral, and we can integrate that accordingly. But when it comes to Green's theorem, is we'll have a line integral, not from one end to the other end, but it encompasses a whole region. So this line integral C, or this curve C, encompasses an entire region D. Okay. So this represents, so we have a line integral that represents now a double integration. What's going on, right? So now it's represented X and Y using our region D. Okay. And this is what a nice green thing represents, is how do we go from one integral to two integrals and vice versa. We can go in both ways, one way to the other way. Now, before we go any further, describing Green's theorem, there's a couple of things also applied going forward. And that's something called a positive or a negative orientation. Okay, so we say something is a positive orientation if the curvature is going that way, meaning the curve is going in this direction as you go around the entire region, like that. So this is when we were having a positive orientation. So you can think of it just like theta, right? So when it comes to the angles, positive theta goes this way. So therefore, going in the opposite direction, hence why theta goes in this way, we have a negative orientation. So now if our curve C goes in this direction, this is a negative orientation. And this will be much more in detail when we talk about surface integrals and we go to Stokes theorems and how orientation goes forwards and backwards in not only 2 dimensions but 3 dimensions with vector spaces. Okay. But for now, we'll just know what one's positive, one's negative, and now we have a line integral that's encompassing an entire region itself. Okay. Well, all these are represented as D for our region. Okay. So now, Green theorem relates both of those concepts. So let C be a positive oriented smooth curve, so we're only going to deal with positive, meaning going in this direction. So in the plane, and let D be the region bounded by C. So this happening, right? D is the region that's created by the line integral of the curve C. And if P and Q have continuous partial derivatives, so meaning you could take the derivative or the partial derivative of P and Q respectively, of an open region that contains D, then our line integral is equal to this, or the double integral of the area. Now, here's a big jump when it comes to this. This is the intermediate step here. This intermediate step represents F, right, with respect to P and the Q. So F is always going to be in terms of P, I, QI, or QJ. And that's how we're going to go back to the double integral. So we're going to find the area of the region there. So finding the area of the region itself over the region, right? Not surfaces anymore, just regions, so for now. Okay. So how does this work? Remember, the whole point of wondering, we always want to encompass line integrals, and sometimes line integrals are really too difficult to actually do by definition. So a lot of times, like Green theorem and then going forward, is how to simplify this much easier way to do so. Okay, that's the whole process of that kind of thing. So for example, let's find the line integral of x to the fourth dx plus xy dy, where C is the curve consisting of the line segments from 0, 0, 1, 0, and so forth. Okay, so we have this going on. So we have 2 line segments going from 0, 0 to 1, 0. So going this way. And then from 0, 1, which is right here, all the way up to, 0, 1, which is right here, and all the way back down there. Okay. So we have segment 1, and segment 2 here. However, is it really segment 2? Because remember, we have a region bounded by this, right? So we have two line segments being connected. So this is technically segment 2 right here, going in this direction. So this is segment 2 and segment 3 technically. So this is the region D we're going to be bounded. So our curve is it's technically 3 segments that creates this region D. Okay? So now, if we want to find this line integral, we're going to break it down to make it using our new equation here, using Green's theorem. Okay, so to do so, we'll do a couple things. So we identify a few things. So in our process, as we can just copy and paste here, this portion right here is going to be P, and this one's going to be Q. That represents our vector field F. So we'll just put P is equal to x to the 4th, and then Q is equal to x, y. Now, according to our formula, right, this line integral will represent this portion. So we'll talk about the double derivative in a little bit over the region, but for now, we can do the easy stuff. So what we're going to do is find the derivative of Q with respect to x, and then find the derivative of P with respect to y. So therefore, I'll just put py, since it's the same thing, it's a partial derivative with respect to y. That's just going to be 0. And then q, I'll just put that in respect to x, that's what that is. So taking the respect to x will just be y. Okay? So these are the two things we're going to be plugging into our integral. Okay? So we're going to have the double integral over our region D of the derivative of qx, which is y, minus py, which is going to be 0, dA. So notice this is actually much easier to deal with, right? So this is the double integral of just y dA, which is, no matter what, a very simple integral to do, even if it's double integration. So, right, so if we had to do this line integral naturally, right, we'd have to convert it, get a vector representation of it, and then figure out from there. We have to maybe break up the line segments. So the whole process of Green theorem is it makes it much easier to look at if the line integral creates an actual region itself. Now we'll just find the bounds. So from that we go back to here. Okay. All right. So we have this triangle here. So remember, it's a double integration. So the easiest way is, let's go this way. So then x is going to be bounded between 0 and 1. And then y is going to be bounded between 0 and this line here. And same thing, where we could find that line. It's y equals mx plus b. And my b is going to be plus 1. And slope is going to be down 1 over 1, so just minus 1. So the line is y equals negative x plus 1. So that is our upper bound. So our bounds are going to be from 0 to 1 and 0 to negative x plus 1 of there. So therefore, our integration is going to be y first, which usually is the case. Okay, so take the integral with respect to y, so it's just going to be y squared over 2, evaluate at 0 and negative x plus 1. So plug in 0 just goes away, so this ends up being the integral, and I'll put the 1/2 on the outside, make it easier, of 0 to 1 of just negative x plus 1 squared dx. Okay. So just like everything else, it's just a quick little u substitution. So divide over gives you negative, so be negative du 1 dx. So this ends up being, I'll put it up here. So quickly u substitution, the integral of u squared, which means is u to the 3rd over 3. So it'll be negative 1/2 of negative x plus 1 cubed over 3, evaluated at 0 and 1. Okay. So I'll bring this outside, so it'll be negative 1/6 times this Okay, so let's see. So negative 1, 6 times, plug in 1, that gives me 0, minus, plug in 0, that gives me, that's 1. 1 to the third power is just 1, so I get 1 there. So negative negative makes it positive, so this is now 1, 6. And there we go. So let's try another example using the same process. So something that looks very complicated to do now. So we want to find the line integral of this, where C is a circle of x squared plus y equals 9. So right off the bat, hopefully you notice we're probably going to go into polar because we have x squared plus y squared. Okay. But before then, we'll just break it down. So we want the line integral. So going back to our definition, we have to identify this is P, this is Q. So what we care about is the partial derivative with respect to y and the partial derivative with respect to x. So taking this whole thing and taking the partial derivative with respect to y, notice that goes away, and we're just left with 3. And then taking the partial derivative with respect to x, notice all of that is gone. So it was just 0 this time. So this is now going to be the double integral over region of this minus that. So 0 minus 3 dA. Okay. So now since our region is a circle of radius 3, we're going to convert everything to polar coordinates. So when it comes to the polar coordinates, so therefore our radius is going to go from 0 to 3. And since we're going the entire unit circle, right, there's no like one quadrant, two quadrants, we'll go, oh, this is going to be from theta is going to go from 0 to 2 pi. So we have the double integral of negative 3r, because we've converted everything to polar, we have to convert that to polar. So that means we multiply by the r itself. And now it's a simple integration. Okay. All right, so let's just integrate this. So this becomes negative 3r squared over 2. Evaluate 0 and 3. All right, so plugging in, this gives me 9. 9 times 3 is 27, so negative 27 over 2. And then we integrate this from 0 to 2 pi of d theta. So this just ends up being negative 27 pi. Good. Okay, now when it comes to Green's theorem, quick little bit of notation before we go any further. If our region D is a circle itself, right? So if this curve encompasses a circle, so our region D, like here, our region D is a circle. We have a quick little notation purposes. Okay, so if D is a circle, then we write the line integral, meaning like this, to convert it to look like that. So we just have a circle representing as C is the actual circle representation. So I can rewrite this entire question to look like this. And it means the same thing. Like that. So these two mean the same thing. Again, the only difference is this statement states that this the curve C gives a region of a circle. Okay. So therefore, now that we have that notation, we can also find the area of this region as well. So kind of like going backwards. So The good thing is, right, it's an area, so it's just a single integration, not a double integration. So if we want to find the area of the region that's this curve is created for it, and in this case, like a circle or a type of circle, we'll talk about that, what it means by in a little bit, is the area is going to equal to the line integral of the curve of x dy, which is the same as equal to y dx, so it doesn't matter which one you convert. However, the proper one, if you put them both together, looks like this. Okay. So this is how we're going to find the area of our region D, created from our curve C. All right. So what I mean by somewhat of a circle is because an ellipse is somewhat of a circle. So we could technically do this process as well. Okay? So we want to find the area of this closed ellipse circle. So just in case, right, an ellipse is kind of like an oval itself. So kind of like that. So it's not perfectly circular like a circle is, but again, somewhat similar, right? You're just stretching it apart. Okay? So it means like kind of similar. Now, because it's somewhat similar, that means we're going to go straight into polar when it comes to this conversion here. All right, so that kind of makes sense. Now here we have a problem because when it comes to ellipse, we actually don't really have a radius. We have two different types of radiuses. So we have the radius going from there to there, and then from there to there. So from two different points going on. And this represents the A and B value itself. So a quick little general equation of an ellipse looks like this. Okay, where A represents the length from here to here, B represents the length from there to there. And you can flip them around, it's y equals this way or that way, right? But that's a general form of it. So, but for our cases, we're going to state that x is going to equal to the, let's say, the radius of the x value, so it's going to be just going to be A, in this case, 4 cosine, we'll just use t since we always use t. And then y in this case is going to be the square root of this, which is just 5, or the radius of the y value, the y direction. So it's 5 sine t. Okay. So now that represents this value there and there. So now we're just going to find dy and dx. So dx is due with respect to cosine, so we negative sine. And same thing over here. Take the derivative with respect to t. This is going to be 5 positive cosine t. So now our area is going to be the line at 1/2 times the line integral, what we have, and plugging in everything we have accordingly. So it's going to be x, so 4 cosine t, dy, which is going to be 5, where is it, 5 cosine t, minus y, which is 5 sine t, times dx, which is negative 4 sine t. Okay, and this is d. Okay, so putting this together, we're going to get, so this is going to be 20 cosine squared. Negative 9 makes positive. 20 sine squared. And look at that. That's going to be a very nice integral. And we're going to integrate just one bound, right? So t is going to go, since it's an ellipse, technically a circle. So we know t is going to go from 0 to 2 pi, going all the way around the entire technical circle. And this 1/2 on the outside. Now, as you can tell, you can probably see what's going to happen, right? Cosine squared plus sine squared equals 1. So we're just going to integrate. 20 divided by 2 is just 10 dt. So this just gives you 20 pi. All right. So, fun little fact about Green's theorem, because actually Green's theorem doesn't just apply to just closed surfaces. What I mean by closed surfaces, we have an expectation of it. So, let's suppose we have 2 or even 3 curves put together. So let's say we have this curve here, which this orientation, this is, we'll say C1. And then we have this other curve, like that. But they kind of connect, like right there, right? So they're right on top of each other. So this is curve 2, going in this direction, right, this way. So as I go along this way, right, that means I'm going this direction up here, back down this way. And this way, I go this way, and I'm going back down that way. So you notice they do in opposite directions over here. Okay? So if I go this way, I'll say this is C3. And since I'm going the exact same path, that means it's just going to be minus the opposite of C3, right? Just negative of the other way. Now the cool thing is, right, when it comes to Green theorem, is we could put both of them together. In other words, the entire region, so this is, let's say, D1 region here and D2 region. If I want the entire region, or D total, is just a union of D1 and D2, which makes sense, right? That's just 2 regions put together. I want the whole region all together. Now the nice thing is, because these are opposites of each other, they'll literally cancel each other out. Meaning if I want to take the line integral of C1 union C2, of this is ends up being the exact same process. Again, the reason why is because the C3 and the negative C3s literally just cancel each other out in this process. Okay. So Green theorem could be actually more applied to it. That's the way I'm trying to get to it. You could do extra stuff on top of that. Okay. In a little bit, you're going to see, well, what happens when we have holes as well. It doesn't always have to be now a nice closed surface. But for now, let's do another quick little example illustrating that portion where we have joint stuff together. Okay. So let's suppose we have this function, this line integral we want to do, and where C is bounded by the region D in the upper half plane, bounded by the 2 curves, where the radius is 1, well, this is supposed to be equal to, and 9. So, quick little sketch of what's going on here. So this is our region D. And this goes from 1 to 3, all the way around. So again, polar is going to be the way to go, right? So this is going to be P, this is going to be Q. Okay. So this is kind of similar to what we have here, right? We have this region here and the region on top of it put together itself. We have like an empty space. And in a little bit, you'll see if we can actually do the entire circles when it comes to closed regions with holes, which means the exact same process, which is actually pretty cool. So this is like the half of what we're about to do. So for now, we'll just break down what we have. So first, we have P equaling y squared, and therefore Q is equal to 3xy. So therefore, we take the partial derivative of P with respect to y, and that's just going to give us 2y. Partial derivative with respect to x, that's just going to be 3y. So everything's in terms of y this time. Okay, so polar coordinates is going to go, so this is just going to be r is equal to 1 and r is equal to 3. So r is going to go from 1 to 3. And then theta is just going to go from 0 to pi, since we're only going to go half the circle. Good. All right, so now we have that going. So let's go back over here. So we're going to have the double integral of our region of Where's it? Where am I drawing a blank? Where's our equation? Oh, yeah, it is. All right, so it's going to be this minus that. dA. There you go. That's our equation. Which is nice because that just ends being A, or in this case, Y. Okay? So now converting everything to polar. So we're going to take the double integral, convert to polar, so Y is going to be R squared sine theta dr d theta. Okay, so integrating that, this is going to be r to the third over 3 sine theta, evaluate 1 and 3. So this is going to be 27 over 3 minus 1/3, all times sine. So that's 26 over 3. And integral of sine is negative cosine, so just give me 26 over 3 of negative cosine theta, evaluated at 0 and pi. Okay, so cosine of pi is negative 1, so negative makes it positive. Cosine of 0 is positive 1, and times this is going to be negative 1. And negative 1 times negative 1 gives, or sorry, negative makes it positive, so it's going to be plus 2. So it'll be 2 times all of this, so it's going to be 52 over 3 as our answer. So we wanted the entire circle. We just double it, right? We just know we're going to get the lower half. Okay. But what Green's theorem actually tells us exactly that. So Green's theorem says, well, what if we have this situation happening, but the entire thing itself? Meaning if we have a region, D, where it's encumbered by this curve here, going in this direction, and we have another curve inside. This is C2, where we actually have a hole, kind of like we have here, right? It's basically, a jagged circle. If you take topology, you'll notice that these two things are basically, this and a donut and a circle, pretty much the same thing, ironically. But how does this work? Or how does this process actually work, right? So again, we want the whole thing, so right? So let's suppose we cut this in two parts. So we have the same surface, or sorry, same region, D, but this time because we have this portion here where this is going this side, and if I just cut this in half, kind of like we did up there, well, when we go this way, it's going that direction, and it's going in that direction, this curve here, going around in this direction as this curvature is, so this way. This represents C1 still. And then going this direction, therefore we're going this way. This other curve C2, so it's going that way and that way in this direction. Notice again the inners actually cancel. So therefore again, the entire region is still the union of both of them put together, which is what we just talked about above. Which means this integral is equal to the sum of its parts. So it's equal to the first one going from down here in that direction. So the line integral of C1 of P dx plus Q dy plus the line integral of this second curve going all the way around. Which is nice, right? We'll just sum them up. However, this is where the cool part is. It doesn't matter which orientation you go, because we found out about independency curves. This whole thing, so this sum over here, ends up being just one straight integral. We just go the entire portion just like it is before. We'll just take it, and these two end up being pretty like itself. We just double it. It's kind of like the theory we had up here, which is a nice thing, interesting part, right? So Green's theorem is actually pretty interesting once it gets to like three-dimensional spaces and two-dimensional spaces, or like you have random objects with holes, and it actually works if you have even higher holes. So some theories of hole theory kind of looks like this. Or this is now how you find the regions and areas of these regions using Green's theorems to break it up, and you end up finding the same result either way, which is pretty cool to signify that.